understand aromaticity, etc., etc. So we're going to do alcohols and phenols and be able to use the word aromatic and have it mean something to you. Alcohols basically is a functional group that's OH, oxygen and hydrogen. These are just some examples of common biomolecules. This is beta-D-glucose. It is a polyalcohol. It exists in a cyclic form like this. We will call this a hemiacetal. When we do the chapter on carbonyl compounds, you'll realize that this is in equilibrium with an open chain form. This is the anomeric carbon. Ethanol, of course, we all know. This is cholesterol. Nice flat molecule. Functional group is an OH. Very, very hydrophobic. Again, alcohols are just the organic equivalent of water. And you can view a whole lot of their reactions just thinking about what would hydroxide do. Common alcohols. This is isopropyl alcohol. We're all familiar with that. 2-propanol is its proper name. This is tert-butyl alcohol, tert-butyl group. Again, this is 2-methyl-2-propanol. Glycerol, this is the backbone for fats, etc. It's a triol. Allyl alcohol, this is 2-propene-1-ol. You remember that a carbon adjacent to a double bond is referred to as an allyl carbon. So this is allyl alcohol. Benzyl alcohol, this is our benzyl group, also properly referred to as phenylmethanol. The names that I've shown here, the common names, are really in use, and you should be able to recognize molecules by either their real IUPAC name or by their common name.
I have a question.
Sure.
For that last one, for the benzyl alcohol, does the CH group always come first?
Yep.
So it would never be where the oxygen is
That would
attached.
be a secret.
Oh,
That's called chemistry. We'll do that next chapter.
okay.
All right, whenever we do a new functional group from now on, we're going to start off with a very brief nomenclature exercise. Just like on your exam, the nomenclature is not a huge part of the course anymore. We're going to deal more with reactions and synthesis, but we have to be able to describe what we're talking about. The functional group, we drop an E from the alkane for a simple alcohol and simply add OL. Again, the alcohol is a high priority group. So we want to identify the parent chain that contains the OH group, number one. And number two, we want to give it the lowest possible number. So it's high priority. Again, just like always, once you identify your chain and you identify your substituents, you just write your name, listing them alphabetically. Do a quick, simple example here. Let's look at this guy. This is an alcohol, isn't it? We could start numbering at either end, but we want this to be our parent chain because it has the OH in it. We want to give the hydroxyl group the lowest possible number, which means we're going to start numbering here. That makes us a 2-all, doesn't it? Finally, you look at your substituents. We have methyl groups in 4 and 5. Our alcohol is in carbon number 2. This is a hexane, so it's going to be a hex and all. Drop the E, put an OL. And we could write this as our name. 4,5-dimethyl 2-hexanol. Any questions? Here we have a difunctional molecule. Again, the hydroxyl group is going to be our highest priority. We want to number the thing so that we get our lowest number at the first point of difference. Okay, that's one of our rules. Our parent chain is going to go along here. So this is a 1, 2, 3, 4 carbon chain. If we let this be carbon 1, that's going to give us a 1 bromo in our name. So that's good. So we have a butanol. OH group is in carbon 2, so it's a 2-butanol. And there's a bromine attached to carbon 1. 1 bromo 2-methyl 2-butanol, or quite often if you have multiple functionalities, you will take and move the 2 from here to just before the OL. So if we had something that was an alkene and an alcohol, we can number the alkene. We're still going to end in OL, but just put the 2 here in between the parent and the functional group. Either of these is acceptable. This is probably the easiest, and this is what I would recommend for the course. Any questions? Well, let's go ahead and just do some examples. Here are some structures. Quickly jot down some IUPAC names. Our first one is a cyclohexane. It has 2 alcohols on it, doesn't it? So we're going to call that a diol. Okay? 2 ols. They are at positions 1 and 3 on the ring. And how about their stereochemistry? It's shown here, so we have to say it. Well, they're both equatorial, aren't they? Think about your ring plane. Are they on the same side of our ring plane or on opposite sides? Try again.
Oh, okay, okay.
They're both pointing down, aren't they? So they are cis. So we would call the cis 1,3-cyclohexane diol.
Oh, okay.
Now here we have a benzene ring attached, don't we? But remember, the alcohol is going to be attached to our parent for this high priority. We want to give it the lowest number. So we're going to start numbering out here as 1, 2, 3, 4, 5. So it's a pentanol, isn't it? It will be a 1-pentanol. And what's attached out here at carbon number 4? It's a phenyl group, isn't it? Remember, when benzene is a substituent, we call it a phenyl group. 4-phenyl 1-pentanol.
Question.
Yeah.
You made benzene a substituent because of the OH?
Yep. The hydroxyl group is the highest priority.
Okay.
So it wins.
5-phenyl?
No, carbon 1, 2, 3, 4.
Oh yeah, that's what I'm saying.
Now, back in the old days when we did cyclohexane derivatives, we had a rule of thumb that anytime you had two substituents on the same carbon, you just looked at it and said, oh, that's got to be carbon 1, right? But now we have a high priority substituent, don't we? It will be carbon 1, making these two methyl groups out here on carbon 4.
Can you just, one more time, if you don't mind, please, with all due respect.
For which one?
For this, with the OH, can you tell me why I was to number it the way I was to number it?
This guy?
The one above.
The one above.
Thank you.
All right, well, we look and we say we have an OH group, right? That's going to be our high priority. If it's our highest priority, then it must be on the parent chain. So the longest chain, the parent chain, is going to be this 5-carbon chain. On the 5-carbon chain at position 4, we have a phenyl group. So this is carbon 1 because you want to give the high priority group the lowest number. So that's 1 all, that's this, 4 phenyl.
For the last one, we didn't have to say that it was trans.
Nope, because it's new. You have two identical methods, so one's going to be axial, one's going to be equatorial. All right, let's do this backwards. Go ahead and draw 3,3-dimethyl 1-pentanol. Nice 5-carbon chain with an OH at the end. In positions 3 and 4, we will have methyl groups. Carbons 1, 2, 3, 4, 5. And in 3 and 4, we have methyl groups. Start off with your pentanol, and then stick on your methyls.
But then if, excuse me, so then if it had a ring at the end of it, then those substituents would be phenol, not methyl.
If this was a benzene ring, yeah. But it's not.
I see. Thank you.
Cis 1,2-cyclopentane diol. Cyclopentane, we draw a 5-membered ring. We're going to have 2 hydroxyl groups. They're going to be in carbons 1 and 2, and they're going to be cis. Now, there are several ways you could draw this. You could use a true perspective drawing, or you could just be really simple about it and use wedgies. Wedgies are probably simplest. You could do it that way, and that works fine. Again, you could show them both going back. That doesn't matter. But they must be on the same side of your ring plane. 2-phenylethanol. Like deja vu all over again, isn't it? All right, our parent is ethanol, isn't it? So we're going to draw a 2-carbon chain, and we're going to put a hydroxyl group on it. Now what's attached to carbon 2? This is carbon 1, this is carbon 2. Attached to 2, we have a phenyl group. Any questions? parent is ethanol. Carbon 2, we have a phenyl group. Yeah.
So we know that the alcohol isn't attached to carbon 2 because that's where the phenol
Yep.
is attached?
Yep, ethanol is only 2 carbons.
Right.
And the hydroxyl group, because it's highest priority, will be non. All right, these are the ones that we had to start with. Let's just do them backwards. You could look at the answers, but that's no fun. Yeah.
Is there anything that will be higher priority than alcohol
Yes.
that we will learn about?
Yes.
Yes. But for now, it's
For now, alcohol's win. All right, we have cyclohexanediol, 1,3. We have to show cis. We could do that as we did in the first slide using axial equatorial, or we could just use wedgies. Wedgies are simplest. That would work perfectly fine. For phenyl 1-pentanol. Our parent is 5 carbons, isn't it? That's 5 carbons. Then we have a 1-pentanol, and we have a 4-phenyl. Or 4-dimethyl cyclohexanol. Again, you just draw your 6-member granule. In carbon 1, we will have the hydroxyl group. In carbon 4, we will have 2 methyls. Let's do 2 more just for fun. Take these names and draw me structures. We're going to have a pentanol, so you start with a 5-carbon chain. Carbon 3 is in the middle, isn't it? That's where we're going to stick our hydroxyl group. Carbon 2 must be next to carbon 3, and we'll stick a methyl. Yeah.
Are you able to go back to the 4,4-dimethyl cyclohexanol?
Okay, just, I can't, but
Does it have a
sister trans?
pi system?
Sorry?
Does it have a pi system?
No, it's a 6-member cyclohex.
I'm saying,
Oh, you mean, no, it's not benzene. It's cyclohexanol and all. It means it's fully saturated. Look at the structure of it on the first slide. Same compound. All right, pentanol again. Start off with a 5-carbon chain. Find carbon 2. You're going to put an OH group. Find carbon 4. You're going to put a methyl group. And it should look like that. Any questions?
It's on 3 because that's pentanol referring to alcohol. So that's how I.
When you read the name, you see pentan.
Yes.
That tells you 5-carbon parent. Go zig, 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 zig.
Very good.
Then you find carbon 2, on this 5-carbon chain. Stick on the OH. Then you find carbon 4 and put on your methyl. All right, let's talk a little bit about alcohols. Like I said, they are the organic equivalent of water. If you include the two unshared pairs of electrons, we are dealing with sp3 hybridization. Because it's sp3, our dihedral angle here is about 109 degrees, just like it would be in methane or whatever. Virtually all of the chemistry and reactivity of alcohols is going to be concerned with the lone pairs of electrons. Remember, we have two unshared pairs. Because of that, it's a good Lewis base electron donor. Because we have a difference in electronegativity, the oxygen is more electronegative than the carbon or the hydrogen. We're going to have a dipole pulling electrons this way and this way. We have a nice electron-dense oxygen. You'll note that the hydrogen is electron deficient. That's going to make it acidic. And out here we have our carbon, just kind of like me. The thing that alcohols do that is very similar to what water does is that they hydrogen bond. They don't do it as well because, again, in water we have two hydrogens attached and they can both be Lewis or hydrogen bond donors. And the oxygen, of course, is a bifunctional acceptor. So it could, this guy can accept one on each lone pair, and we form these extended networks. Because of that, alcohols are essentially liquid at room temperature, even though they're very low molecular weight. Just like water, hydrogen bonding stabilizes it. Like I said, the OH group, because it's involved in hydrogen bonding and because it's electron deficient, is acidic. It undergoes equilibrium ionization, just like any other acid that you learn in general chemistry. This is the acid dissociation. Ethanol, in the presence of water, will spontaneously dissociate to give ethoxide and hydronium. To write this equilibrium constant, remember from general chemistry, you simply put products over reactants, and you do not include liquid water. Equilibrium expression will look like this: ethoxide, hydronium, and here's our reactant. Even though alcohols are acidic, they are poorly acidic. They are weaker acids than water. Water has a pKa of 14, I'm sure you remember that. Ethanol, this dissociation constant is about 10 to the minus 16, making its pKa 16. So it is acidic, but it's less acidic than water. If you look at substituted alcohols, you can see a range of acidity. All the way here from 18, these are carboxylic acids. Again, we know that they're very acidic. We'll talk about them later. Just focus on the alcohols here. As we go and put electron withdrawing groups on the carbon portion of our alcohol, you'll note that the pKa gets lower and lower. Let's just look at two examples here. This is trifluoroethanol versus ethanol. Very similar in structure. pKa difference of almost 4 units. So big difference in acidity. Now the reason that trifluoroethanol is more acidic is simply that it forms a more stable anion. This is one of the fundamental things about acidity. The more stable the anion, the stronger the acid. If you think about trifluoroethanol versus ethanol, fluorine is very electronegative. Because of that, it's going to polarize all these bonds and have a partial negative charge on all the fluorines. Because of that, it's going to pull electrons from the O- back into this thing. That makes the O- more stable. Therefore, we have a stronger acid. We can see this nicely. If we convert this first to ball and stick, here's our trifluoromethyl group, and then to an electrostatic potential map. Look at the color of the oxygen here and here. Again, the trifluoro group has pulled electrons out of these bonds down towards the fluorine. The more stable the anion, the stronger the acid. Interesting thing about this, because fluorine is so electronegative, we have a dipole in this molecule. It's going to look like this. We're going to pull electrons from here out towards our fluorine. In ethanol, we have just the opposite dipole, where the oxygen is now most electronegative, sucking electrons towards itself. The fundamental thing, the more stable the anion, the stronger the acid. Now, phenols. Phenols are nothing more than a benzene ring with an OH attached directly to it. Phenols are acidic, just like all alcohols are. And if you were to draw or write the equilibrium expression, it'd be the same thing. It'd be products over reactants, ignoring water, and it would look like this. Now, it turns out that because of resonance, the phenol anion is much more stable than, say, the anion in ethanol. Why is that? Because we can move this negative charge into the ring by resonance and stabilize it, disperse the negative charge in the ortho and para positions simply by resonance. Because of that, the equilibrium constant here, Ka, instead of 10 to the minus 16 for ethanol, is down to about 10 to the minus 10. So this is 10 to the 6th, a million times more acidic than ethanol. Now, back when we did electrophilic aromatic substitution, we talked about substituents on the ring and how they can pull electrons or push electrons, right? Well, that shows up in the acidity of phenols. Down here we have methoxy as our substituent. Remember, that was activating, wasn't it? It was activating because it could push electrons into the ring by resonance. The effect here is that this is a stronger acid now, a weaker acid than phenol. If we stick on electron withdrawing groups, like our nitro up here, we know that those pull electrons out of the ring, and that means the anion is even more stable. That means that the pKa of nitrophenol is about 1,000 times, it is 1,000 times more acidic than phenol itself. Any questions? The real take-home lesson that I want you to understand, because we're going to talk about anions a lot in the next few chapters when we do condensation reactions. The thing you want to remember is the more stable the anion, the stronger the acid. Any questions? All right. We use a whole lot of ethanol and methanol. Commercially, you can make what's called synthesis gas by taking coal, convert it to coke, and pass steam over it under lots of pressure. And by gosh, it breaks down into carbon monoxide and hydrogen gas. Once you get synthesis gas, this is actually a very important process, the making of this stuff. Because once you get it, you can do lots of stuff with it. One of the things that they do with it is run it over a catalyst, and they make about 1 billion gallons of methanol with it every year. Methanol is toxic. It is, you should not drink methanol. The reason that it's so toxic is that your body tends to take alcohols and it dehydrates them. I suppose the proper thing is it oxidizes them. It'll convert this into formaldehyde. Formaldehyde is a very reactive compound, and because of that, it will react with the amino groups on proteins and basically cross-link them. It's really bad stuff. Ethanol, which is also made in large quantity industrially, quite often from ethene with water and a catalyst. This is oxidized to acetaldehyde, and your body is actually very good at disposing of acetaldehyde. Formaldehyde, it is not, but this is not nearly as toxic.
So why do they still use formaldehyde?
Why do they still use it? Oh, it's very useful compound.
It's just really dangerous.
It can be dangerous, yeah, but shoot, it's dangerous walking in the parking lot.
Don't you use that to preserve a passed
Yeah.
away person?
Again, why is it preserved? Because it reacts with the amino groups on proteins, cross-links everything, holds it all together. Bacteria can't even eat it anymore. So you have to be careful with it. But it's a very useful compound. Now, because alcohols are acidic, but they're not very acidic, quite often, again, in chemistry, we're going to use an alkoxide as a base to do a reaction. We did this in lab last week. We used sodium methoxide, didn't we? Typically, you would make something like sodium methoxide from methanol, add a little chunk of sodium, it fizzes, we get hydrogen gas off, and we're left with sodium methoxide. Another way to do it is to take a strong base like sodium amide. Now, how do you make sodium amide? It's even more fun. You start off with liquid ammonia, and you add little bits of sodium to that. It bubbles. We're left with this very strong base. This is a strong base because it's a nitrogen anion. Its pKa is up about 20-ish, so it's much more basic than alkoxide. And if you take this, mix it with that, you get essentially pure sodium ethoxide in this case. We can also make what are called alkyl lithiums. We'll see how to do that in just a little bit. Just like we had a bottle of sodium methoxide, you can have a bottle of methyl or commonly butyl lithium, very strong base to make the alkoxide. Now we're going to talk about reactions of alcohols. We already know reactions that yield alcohols, however. So let's go way back into organic 1. These are all reactions of alkenes. We learned very early on that we could take an alkene in the presence of strong acid and water, we could protonate the double bond, and we would form an alcohol. We remember that this is a stepwise reaction. That means it has a carbocation intermediate. Whenever you have a carbocation, we can get rearrangement. That's bad. And when we're all done, the OH group will add to the most stable carbocation. That is referred to as Markovnikov regiochemistry.
Is that for all of those reactions, all four?
No, that's for the first one. A more civilized way to do this that we learned was to use mercury 2 acetate. This gave us an intermediate mercuridium ion, which meant that we did not have a carbocation. If we don't have a carbocation, we do not get rearrangement. So that was the advantage here. Once again, we get Markovnikov regiochemistry. We need to dump in sodium borohydride. We used that last week also. And that reduces off the mercury. If we wanted anti-Markovnikov regiochemistry, we remember we could do this using BH3 in an ether, followed by oxidation with peroxide. Again, this generates an organic boron compound called a borane. The second step here, you're oxidizing the boron off. Nonetheless, you wind up with anti-Markovnikov. It's interesting also that this is cis addition, the OH and the H add from the same face. And finally, we talked about making 1,2-diols. We could do this using potassium permanganate or osmium tetroxide. Osmium is very, very toxic. Permanganate is very, very cheap. Typically, this is what you would do. Alkaline permanganate, a cis 1,2-diol. Nice, simple reaction. Now, all that was review. Today, we're going to talk about ways to make alcohols. We're going to do this using reduction with borohydride or with what's known as lithium aluminum hydride. If we have an aldehyde, we will simply add hydride anion to it and make a primary alcohol. If it happens to be a ketone, we would make a secondary ketone. Secondary alcohol. We'll talk about the hydride reduction. Again, we did a hydride reduction in lab. It's a very nice, very simple reagent. Aldehydes and ketones reduced by either of these. Again, aldehyde, because we have a hydrogen, is a primary alcohol. A ketone, because we have two alkyl groups here, will give a secondary. We're going to look at a class of reactions called Grignard reagents. Grignard reagents, we'll see, are a major feature of Chapter 17. Okay? Grignard reagent is really kind of neat. This is abbreviated here as RMGX, where R refers to the organic chunk. It can be virtually anything. It's going to behave as if it is a carbanion. And we're going to add that carbanion to our carbonyl. If we have an aldehyde, we'll stick on the R group here, convert the aldehyde to an OH. If it's a ketone, stick on the R group, we now have a tertiary alcohol. We'll talk about these in great detail. Any questions, as this is just where we're going?
Would you like to go back to the side note?
To this guy?
Yeah, those are the side notes. That kind of summed up the, yeah.
In a hydride reduction, just like I said with a GRIGNARD, we're going to be adding a carbanion. Using either borohydride or lithium aluminum hydride, we're going to add H minus. The mechanism of this reaction can be thought of like this. This is a model here of lithium aluminum hydride. Lithium is the cation. We have an aluminum here, the little pink guy, and it has 4 hydrogens attached. With something like lithium aluminum hydride, you can actually donate all 4 of these hydrides. Now when we say we're going to donate a hydride, we're talking about the hydrogen and its electrons. So it's H minus. All the world that happens here is that H minus is going to go attack the carbonyl. Now why would it do that? Well, remember, oxygen is more electronegative. It pulls the electrons towards itself and makes this carbon positive. So all we're doing is taking the negative hydrogen, we're adding it to the positive carbon. In order to do that, we have to move these electrons out on the oxygen, don't we? Got to put them somewhere, can't have 5 bonds. So this gives us this lithium oxyanion. Our second step in this reaction is to take this stuff and we acidify. Why do we acidify? Because we simply want to convert this into an OH. So step 1, we take H minus, add to the carbonyl. In order to do that, we have to move these electrons up, and that makes this oxygen anion.
What happens to the aluminum with the H3 now?
Well, we're going to use the rest of those in subsequent reactions. We're just worried with one right now. Once you do this, once you get to this point, we can simply protonate this and wind up with our alcohol. And this is the hydride that we added. Remember, hydrogen with its electrons is a hydride.
Where'd you get that hydrogen from? Where did the protonation come from on the H plus over there?
This, we just dump this into acid.
Okay.
Lithium aluminum hydride is a very, very versatile reagent. In the coming chapters, we will use it in lots of different ways. This is a synopsis of what we're going to do. We just talked about the reaction with aldehydes and ketones. This is primary alcohol. This is secondary alcohol. We'll also see today that we can use this with esters. Later we'll see we can do it with epoxides, nitriles, carboxylic acids, or azides. Very powerful reagent.
Didn't you say that alcohol gets priority? So how's it a
That's a
secondary?
nomenclature.
Oh, nomenclature.
All right, so in this chapter, we're only going to deal with aldehydes, ketones, and esters. Now, we can do these reductions, as we said, using either sodium borohydride or lithium aluminum hydride. Now, like I said, we use sodium borohydride in lab. Remember, it's this white powder, you took it in the back, you weighed it out, Nice stable stuff, dissolve it in water, etc., etc. No problems with it. Lithium aluminum hydride, however, is a very, very reactive substance. You have to do this reaction in ether, but the ether that you use must be absolutely dry. And that's because if you happen to take some lithium aluminum hydride solid and just set it out on the tabletop, now it will spontaneously react with the moisture in the air and burn. So this is very dangerous stuff to work with. Ether is explosive as all get out. This stuff, as soon as it touches moisture, boom, you get flames. So you have to be very, very, very careful. However, sodium borohydride isn't quite as good a reducing agent as lithium. And that's because, well, as example, if we take this conjugated ketone here, in the presence of borohydride, you'll get both reduction of the carbonyl to an alcohol, which is what you presumably wanted, but you'll also get reduction of the double bond. If you wanted that to happen, that would be good, but you probably didn't. With lithium aluminum hydride, much more specific, here we get 94% alcohol and just a little bit of the side product. So lithium is much more dangerous, much more selective. Typically you would use borohydride whenever you can. Now for me to sit up here and say lithium aluminum hydride spontaneously burns, well, that's one thing. This is a movie. This person is holding a beaker that has ether in it.
That's awesome.
Now, ether is somewhat hygroscopic, and if you let that just sit out on the bench for an hour or two, it will soak up water from the air. So this is bad ether. In the hood here, they have a large beaker with a little bit of lithium aluminum hydride in it. So let's see if we can make this work. No, PowerPoint is going to do this to me. Why does it do this? Goes, dumps it in there, and poof.
Because it had water in there,
Because
the
it had
ether was
just
less
a
of a...
trace of water. And it's just, you see the purple flame that's from lithium. And just when you think it's safe, it goes off again, etc., etc. Very dangerous stuff to work with.
There are the candles.
So we're not going to do that in lab. All right, let's just do some very simple problems here concerning reduction. What I'd like you to do is a simple one-step synthesis. So look at the alcohol and just say to yourself, what carbonyl compound did I need in order to make this alcohol? Now, a lot of the things we do is rocket science, but this really isn't. You look at this and say, okay, this used to be a carbonyl. We added H- to it. That comes from our lithium, doesn't it? Therefore, all we have to do is to write our carbon skeleton here and make this guy a carbonyl. Same thing with our next one. We identify the oxygen. This used to be a carbon-oxygen double bond, methyl group on one side, this thing on the other. Oops. Looks like that. And finally, this is a cyclohexanol. Remember, if we number this, this would be carbon 1. This is shown as diequatorial, that means they are trans. But this used to be a carbon-oxygen double bond. Therefore, that would be our thing. Now I said here you'll actually get both isomers because H minus could come in from the top, like it did here, to give the trans isomer, but it could also come in from the bottom, and that would give us the cis isomer.
That's the first time I've seen a double bond like that with oxygen on the foot.
Yep, it's just cyclohexane. We'll do that in chapter 19. This is probably the major product because trans is going to be more stable than cis. Any question on reduction? Again, to do a synthesis, you find the OH group and just say to yourself, that used to be a carbonyl. All right, I said we were going to do Grignard reactions. Just like we added H minus. In a Grignard reaction, we're going to be adding the moral equivalent of a carbanion, C minus. The rest of it is exactly the same. To make a Grignard reagent, you take any alkyl or aryl halide, and that's pretty much any. React it with magnesium metal. You have to do this in an ether. Once again, have to be careful with ether. Do this cold, and you would make, in this case, the cyclohexene magnesium chloride, referred to as an organometallic reagent. Now you have to do this in ether because the reactive thing in a Grignard reagent is actually the Grignard ether complex. Typically you would use diethyl ether. You can also use tetrahydrofuran. That's next chapter.
Refresh my memory, Dr. Young, what's a Grignard reagent? What's that again? Refresh my memory. Grignard reagent.
Grignard reagent is going to react as if it's a carbanion, C minus. We could also do this not just with alkyls, but also with aryl. So here, bromobenzene reacts to give phenyl magnesium bromide. Very nice reaction. Typically, you would make a Grignard reagent immediately before you use it. I believe we will actually do a Grignard reaction in lab. Why do we need the ether? Well, like I said, the ether complexes with the magnesium. And that is the reagent that reacts in the Grignard reaction. This is just methyl magnesium bromide. That's all. This is methyl magnesium bromide. Here's our magnesium right here. But we're complexing the magnesium to 2 molecules of ether. Now, what does that do? Probably you can see it best in an electrostatic potential map. If we just look at this guy, this is no ether, you see we have this carbon kind of greenish, nice negative bromine, or magnesium in the middle here, the metal, is very positive. Over here, the positive on the metal is gone. We have nice negative bromine up here. But the thing you should note is that our carbon here was pale green, and now it's pretty much yellow, isn't it? So by chelating this, making this neutral instead of positive, we wind up with a negative carbon. This is the negative carbon that will react in the Grignard reaction. Now think of this exactly like the hydride, except that we're doing C- instead of H-. If we draw our magnesium or Grignard reagent this way, like we said, the R group, the carbon group, is going to be negative. This end will be slightly positive. Here's our carbonyl. Just like we added the H- to the carbonyl carbon, we're going to add the R-, and we're going to form the same addition product. As this adds, we have to move the electrons up, and that gives us our oxyanion. All right, we take this stuff, we dump it into acid, and we're going to wind up with the alcohol. Just like we said that lithium aluminum hydride was very versatile, Grignard reagents are also versatile. We're going to talk about these reactions of Grignard in this chapter. If we react a Grignard with formaldehyde, we will make a primary alcohol. Aldehydes will give us secondary alcohols. Ketones, tertiary, and we'll see later that esters also give us tertiary alcohols. So let's just go ahead and do a simple one here. If I have formaldehyde and I react it with cyclohexane magnesium bromide, draw me the product. Remember, step one, this is going to be a carbanion, isn't it? The carbanion is going to attack the carbonyl, and the electrons are going to go up. We will make the simple oxyanion. When you do a Grignard reaction, you always have a second step. After you make this stuff, you take it and you dump it into aqueous acid, a little bit of HCl. And we wind up now with the primary alcohol. The CH2 is this CH2 from formaldehyde. Let's do it with an aldehyde. Look at your Grignard reagent. The carbon that's attached to the magnesium is going to be our carbanion. So this carbon is going to attack the carbonyl. The electrons will go up. And we will get this as our intermediate. Now at our final product, we're going to have a chain of 1, 2, 3, 4, 5 carbons with the OH in carbon 2. Once again, in words, aldehydes, secondary alcohol. Ketone. Our methyl group is going to be the anion. It's going to add to the carbonyl carbon. So up here, going to move the electrons up. Now we're going to have a carbon chain of 1, 2, 3, 4 carbons, OH in carbon 2, and a methyl in carbon 2. We have taken a ketone and we have made a tertiary alcohol. I will hush for a second. Draw the structure.
Forgot to set an alarm. I'll sleep at 10 o'clock last night.
The methyl is our carbanion. We're going to add to the carbonyl carbon. Doesn't matter that it's in a ring. That will be our oxyanion. The oxyanion will be protonated when we dump it into water, and we will make the 1-methyl cyclohexanol. You feel so good when you get it right, I know. The organic is so much fun.
Put it back real quick, Dr. Gill. I missed the last. Can you put it back, please? See. Okay, that they use
1-methyl cyclohexanol. Benzaldehyde. It's an aldehyde. Say to yourself, the aldehyde is going to give you a secondary alcohol, isn't it? Methyl group's going to add to the carbonyl. That will be our addition intermediate. Dump this guy into water. And that's our product. Now, if we were to name this guy, what would we do here? OH must be on the parent chain, right?
Yeah.
So this is our parent chain, the 2 carbons. It's an ethyl. And now our phenyl group is attached to carbon 1. So this would be 1-phenyl ethanol. Do one more here. Phenyl magnesium bromide. We have acetone, which is a ketone. The phenyl anion here, that's our CH2. It's going to add to the carbonyl carbon. And that's our anion. Dump this guy in water. Gonna protonate the O minus. Now our parent chain is 1, 2, 3 carbons, isn't it? So it's a prop,
Why isn't it in the middle? Why did it like,
because it adds right there. Add to the carbonyl carbon. Methyl on both sides. Our name here, this would be a prop. It would be a 2-propanol, 2-phenyl, 2-propanol. All right, go ahead and do a set. Now this set of slides is color coded to help you visualize where the pieces are coming from. Our methyl group is going to be our nucleophile. It's going to add to the carbonyl carbon. If you look at our product, this is the part that came from the aldehydes. This is the part that came from the GRIGNARD. Our next one, our phenyl anion is our nucleophile. It will add. The phenyl group came from the GRIGNARD. The rest of these carbons came from a ketone. This is a pentanone. Carbonyls in the ring. Again, the 2-propyl anion is going to add to this. Here we stuck on the 2-propyl group as our GRIGNARD. The rest of this comes from the carbonyl. So when you work backwards, all you do is just look where the alcohol is attached and just say to yourself, this carbon used to be a carbonyl. That's all you have to do. Very quickly, just run through and do these. Methyl group will add to the carbonyl carbon. This is going to wind up as an OH. We will have 2 methyls and a hydrogen attached. Again, we have an aldehyde. The phenyl anion is what's going to add. Going to add here. This is going to be an OH. We will have a methyl group and a phenyl group and a hydrogen attached. They're not on any set? Oh. Well, write them down. The cyclohexane anion is your nucleophile. We'll add to the carbonyl. This is going to be an OH. We will have a methyl, and the cyclohexane attached to it. This set isn't in your handout, I'm sorry. Oops. But I believe the recording is working, so we're in good shape.
Yeah. I gotta go to work, Dr. Gunn. I'm gonna listen to this on the internet. Thanks.
Okay. All right. The neat thing about a Grignard synthesis is that for every Grignard synthesis, you can do it 2 ways. Okay? Let's say I asked you to suggest a synthesis to make this thing. How would you make this in a Grignard reaction? Well, what you want to do is look and see, all right, where is the oxygen attached? There, right? Now, a long time ago, that used to be a carbonyl, didn't it? And we added a carbanion Grignard to it. So if this was a carbonyl, this could have been our Grignard, couldn't it? So you start off with where the oxygen is, and you say, I'm going to split on this side. Now, this then used to be my Grignard, and this used to be my aldehyde. You know it's an aldehyde because it's a secondary carbon. So, quickly, write down the reagents that you would use to make this. The Grignard reagent is just going to be our phenyl group, isn't it? So that would be phenyl magnesium bromide. The carbonyl half. This is going to be a carbonyl. It's going to be an aldehyde. It's going to have a 1, 2, 3, 4 carbon chain and a methyl group. Therefore, the pair would look like that. Here's our aldehyde, our anion adds, and we make this.
It doesn't have to be MGBr, it can just be VR. Oh, I'm sorry. I didn't see
Yep,
the
there's our
VR.
magnesium there. All right, that's one way to make it. What if I would have split on the other side? So again, let's split here. What pieces would we need if we split here? Now the carbonyl is on the side here with the benzene ring, isn't it? And this stuff right here, this carbon fragment, was our Grignard. So the pair would look like this. Carbonyl side is simply benzaldehyde. This side is simply this carbon fragment. This works for every Grignard synthesis. You can make it 2 ways. Oops. Now we're going to practice this because this is a very important skill. Take this guy. What I want you to do is give me 2 sets of reactants that will give me this alcohol. You know that we're going to deal with aldehydes because it's a secondary alcohol. split it on each side, figure out the structure of your Grignard and the structure of the carbonyl. Find your carbon bearing the alcohol and a split on one side. This was the aldehyde. This 2-carbon chunk was the Grignard. 2-carbon chunk is an ethyl. Here we have an aldehyde with 1, 2, 3, 4 total carbons. Split on the other side. Here. These carbons were the aldehyde. These carbons were the Grignard. Our Grignard contains 1, 2, 3 carbons. Our aldehyde has a carbonyl and a 2-carbon chain. Three carbons, aldehyde with a 2-carbon chain. Now that's simple, isn't it? And it's fun. All right, the last Grignard reaction we're going to talk about in this chapter is the reaction of a Grignard with an ester. An ester is different than ketone or an aldehyde because it's going to add 2 moles of Grignard. The mechanism that we're going to see on the next slide is important to think about because in chapter 19, 20, 21, whatever, we're going to deal with a lot of these addition, elimination reactions. So, let's look at a simple carboxylate ester. Now let's start off just saying, okay, well that's a simple ketone or a simple carbonyl. We're going to add our methyl group to it. But like I said, in an ester, we actually do it twice, and we're going to lose the whole oxygen thingy. So we keep the carbonyl half, and we add 2 moles of Grignard to this carbon. Well, this is the bottom line of what happens. We add 2 moles of Grignard, that's these 2 methyls, and we keep carbonyl carbon and whatever else was attached, which just happens to be a methyl. Now let's look at the mechanism and see how this happens. Step 1, we're going to take, just like we did before, bring a Grignard up to it and let it add. Remember, our Grignard is a carbanion, acting as if it's a carbanion. It's going to add to the carbonyl carbon, just like this, and we're going to get an addition intermediate. Now with a ketone or aldehyde, it stops here, doesn't it? But the thing that makes an ester different is that this electron pair We pushed it up when we did the addition. This electron pair can come back down to form a double bond. And when it does, it has to push something out. So this is an addition step. An elimination step. We're going to move these electrons back. And we're going to kick out our leaving group. Addition, elimination. Once again in chapter 2021, we're going to do this so many times that you're going to go blind. But this is our first introduction. If you have a leaving group, that's something that can leave, it will. Why does this leave? This is alkoxide. Remember, that's a fairly stable base. It certainly is much less basic than a Grignard. Now, what have we just generated when we did this? We made a ketone, didn't we?
Yeah, yeah.
And what's a ketone do? It reacts with another Grignard. And we wind up now with our tertiary alcohol.
So where did the other oxygen?
No.
Where does it go? You flush it down the drain.
Okay, so we don't have to do plus.
Nope, nope, it's gone. You dump it down the drain. If you have an ester, you're going to add twice. Now we'll do some problems practicing this, but that's the simple bottom line. You lose everything that's in the ester portion, keep the other half, and add 2 Grignards to it. So what you remember here, Grignards add to aldehydes and ketones to form secondary, tertiary alcohols. They add twice to esters to form tertiary. Now, Grignards are not perfect. Because this is a carbanion, it's a very strong base. So anything that is acidic, it will react with. That means if you have any of these guys in your compound, not going to work. Immediately, that's going to, say we had methanol, going to react, or methane with the hydrogen on here, and methoxide. So that isn't going to work. There are also other reactions, and we're going to cover these in later chapters. They can be useful. But if you happen to have any of these guys in your compound, once again, you can react with a Grignard. We can use these usefully, but right now we have to just be careful. So nothing acidic, basically nothing else with double bonds except an alkene. Any questions?
You should accept the what?
I'm sorry?
Nothing.
Except for alkenes, right? Double bonds. All right. We're going to see a bunch of these later. This is a problem that will appear on your next exam and will appear on your final. Here you have a selection of compounds, and you are simply asked to do a Grignard synthesis. I would probably ask you to do it 2 ways. Okay? So pick out each carbonyl and or each Grignard from up here. These are all carbonyls, so we have to just deal with those. All right, step 1. Go ahead and look at this. Try to figure out what pair you would use to make this compound. What pair you could use. as you look at here, there's a whole selection of all sorts of stuff, right? But what you have to remember is we're going to need a 3-carbon chain carbonyl here, correct? So you can pretty much narrow this all down to just a couple compounds. Those 2 esters are the ones that could work. Now, because they have the straight chain here. This guy has the appropriate number of carbons, but it's an ester, isn't it? This, we're going to lose the ester portion and keep the hydrogen. That's okay because we have a hydrogen here. Okay. Our top one, because it's an ester and a simple Grignard, would give us a tertiary alcohol, wouldn't it? So this, even though it has the right side chain, instead of the hydrogen here, we would have another 3-carbon chunk hanging down. That's not going to work. This guy, on the other hand, this is the hydrogen that's going to show up here, which means that each of these was added from a Grignard. We're going to split on both sides of our carbonyl. This is what's left of the ester, just the hydrogen and the OH. And these are the chunks that we added from our 2 moles of Grignard. Therefore, this was our compound. Our Grignard looks like this. Now, if you've noticed at the end of this set of slides, there are like 3 or 4 of these. We're going to exhaustively get through the rest of the chemistry in this chapter. Then we're going to break for 10 minutes. You can work on that set, and we'll do this set of synthesis reactions. Any questions? Well, like I said, there's a whole lot of material in this chapter. We've done hydride reductions. We have now done Grignards. There is another anion that is commonly used, and that is an alkyl lithium. If we take an alkyl halide, not just limited to alkyl, this can also be aryl, so like benzyl bromide, or it can be vinyl. It can be attached directly to a double bond. So very versatile. And we react this with lithium metal, once again an ether. We form an alkyl lithium. Just like a Grignard, this is a carbanion. And just like a Grignard, it's going to add to a carbonyl. So I hope you figured out a theme for this chapter. We're taking anionic things and simply adding them to carbonyls. An example. Here we have acetone. Here we have just a generic R lithium. R minus is going to add to the carbonyl. Going to make our addition product, the O minus. This thing we would then dump into water. It would protonate and make the alcohol. Any question? Same basic reaction. Go ahead and do this one. This is a vinyl lithium. So originally, where the lithium is, there was or chlorine. React that with lithium metal, lithium replaces the halogen. Reacting this with benzaldehyde. Now the reason that this is, on the slide here, is that it's a little difficult to draw the structure of the product properly. But just think about what you're doing here. All you're going to do is take this as a carbanion. Right? That's where the negative charge is. That's going to form a bond with the carbonyl carbon. Here's our carbon. This is our anion. It's going to simply attack. Eventually, we will pick up a proton here, so this will be an OH. The product will have the OH, hydrogen, a phenyl, and a bond to this carbon. Here's our OH, hydrogen we don't show, a phenyl group, and a bond to this carbon. So make sure you can figure out how to draw this. Now you can see it. It's a little bit of a tricky structure to draw. All right, let's do a quick set of these. Just draw the structure of our final compound. Oops. All right, in our first one, this is our carbanion, the methyl group. It's simply going to add, this is going to be an OH, methyl group attached, hydrogen attached. The methyl we just added is simply 2-propanol. Okay. This is a Grignard reaction. Same thing, isn't it? This is our carbanion. It's going to add to the carbonyl carbon. We're going to have an OH, 2 phenyl groups, and a hydrogen.
So we don't have to draw the extra hydrogens, they should
Nope.
just be implied.
Don't have to, you can. If it helps you, do it. Formaldehyde. Our carbanion is going to add to the carbonyl carbon. We will have a CH2OH.
Wait, I have a question.
Yeah.
Oh wait,
Don't understand what?
The last
So
one.
we keep
The
that
last one. Our carbonyl has 2 hydrogens attached, right? They're gonna stay there, so that's a CH2 group.
I just drew different.
Yeah.
Thank you.
All right, do this again.
That's advanced discount.
In our first one, we look and say this is an ester. What do we do with the oxygen half of our ester? We wash it down the drain, don't we? It's gone. Only thing that's going to remain is going to be this as an OH, whatever's attached here. We have methyl as our Grignard. We will add 2 methyls right here and simply make butyl alcohol.
Why do we lose that ring?
Why do we lose it?
Yes.
Remember, everything, this whole chunk is our leaving group. It's gone. We washed it down the drain. This next one is again, an exercise in drawing the product. Our carbanion is the alkyne anion right here. We're going to form a bond between our triply bonded carbon and this guy. This is going to be an OH. We have a hydrogen attached and a triple bond. This is the bond we just made right here. This carbon going to form a bond from this carbon to this one. That's this one. This is the bond we just made. Carbonyl is now an OH. Yeah.
What did you lose from this one besides the NGPR? Or did you not lose anything else?
Well, to make this, we started off with a triple bond with a bromine attached. Reacted that with magnesium. So this is our carbanion. That's where it attacks. We have a vinyl lithium. This is the carbanion. It will add. This will be an OH. Methyl group attached, hydrogen attached, and this whole thing attached to this carbon. The bond we just made is this one right here. All right, now we're going to move out of the business of adding carbanions. And we're going to do just a few reactions of alcohols. Once we make the alcohol, what can we do with it? Turns out we can do a lot. One of the important things that you can do is convert an alcohol into an alkyl halide. Now you can do that a couple ways. Probably one of the crudest ways is to simply take an alcohol in the presence of HCl as a gas, in ether, nice ether solvent, always works, do it cold. This only works with tertiary alcohols, however. That's because this is a carbocation reaction. We're going to have a carbocation intermediate. If we didn't have a tertiary alcohol, we would have rearrangement. And of course, we're going to wind up with a Markovnikov product. That is, the halogen will attach to the most stable carbocation. So this works, but only with a tertiary alcohol. That's a crude reaction. If we wanted to do this in a nicer way, we can use what's known as PBr3, phosphorus tribromide. Phosphorus tribromide in ether will take a simple alcohol, primary, secondary, and convert it to an alkyl bromide. Now that's the basic reaction you need to know. But how this thing happens, it's actually two-step. First thing we're going to do here is use our oxygen as a nucleophile with the phosphorus, and we make this phosphate ester, phosphite ester. We can actually add 3 of these to our phosphorus as our intermediate. But the thing that's cute about this is that in order to get your alkyl halide, the bromide that we kick out when we make our bond here acts as a nucleophile in an SN2 reaction. Remember those? So this guy comes in, attacks, our phosphite leaves. This is an SN2 reaction. And what do we remember about those? If this was a stereocenter, that is a chiral carbon, this would go with inversion of configuration. SN2 reaction, inversion of configuration. Let's just show that. Now this is what's known as a Fisher projection. We'll get to those towards the end of the course. It's a shorthand way of drawing stereochemistry. In a Fisher, these guys that are the horizontal bonds are coming towards you. So this relays stereochemistry. Top 2 are going back. These 2 are coming towards us. Thionyl chloride impurity does the same thing as PBr3 does. Pyridine looks like this. It's an aromatic heterocycle. We'll use pyridine a lot for things. Pyridine is basic because it's an amine. It's probably most notable because it really stinks. Really stinks. You don't really want to mess with it too much. But thionyl chloride and pyridine, just like with PBr3, the oxygen is going to attack the sulfur, and we're going to make the ester. Now, just like with PBr3, second step is SN2. This is going to attack. This is going to leave. But because we have a stereocenter, what we have done is we have inverted the configuration here. So if this guy was R, this guy would be S. Now this is neat, actually, as you're doing more sophisticated synthesis, because this means we can control the stereochemistry at a site if we need a certain stereochemistry. So PBr3 and thionyl chloride and pyridine both give inversion. If we wanted retention, we can do another thionyl chloride reaction in something like ether or benzene or carbon tet, a nonpolar solvent. Here we're going to do the same thing, make the same ester intermediate. But because we're in a nonpolar solvent, say pentane, there's no chloride floating around here, is there? It just bubbles off as HCl. So the only way you can get product is from this chlorine here. What happens is a rather remarkable reaction where this chlorine just kind of slides down as it leaves, called an SNI reaction. It's an example of a front side attack, but because it's front side, it gives retention of configuration. So the neat thing here is we can actually control that. The two reactions that you need to know for conversion to halides are going to be PBr3, thionyl chloride and pyridine. Those both give inversion. Thionyl chloride nonpolar gives retention. We'll do some problem sets later that have examples of the stereochemistry. The next reaction we want to do is conversion of an halide to an alkene. Now this is the brutal version, just like HCl and ether. We can take this, convert it here. Again, it's a carbocation intermediate. Again, we're going to get rearrangement. Again, it's not your first choice. We're probably going to do a reaction like this in lab. Very brutal, but that's because the reagents are cheap and it's simple. If you want to do this in real life, you would do something like POCl3. Again, it's a phosphate compound. And pyridine again. This reacts very, very nicely to give a simple alkene. Reaction here. We're going to generate, once again, our phosphate ester. The reason that this works so nicely, though, is that the second step here, pyridine, does an E2 elimination. Now, what do we remember about E2 elimination? Sate-Sef rule, most highly substituted alkene, so we get this one, not this one. And just, we do a nice trans elimination. So this gives intermediate E2, Sate-Sef's rule, trans elimination. So we've done alkyl halides, we've done alkenes. One other class of reaction we need to talk about, and that is simple oxidations. We've taken carbonyls and we've made alcohols, right? Now we're going to go backwards. We're going to take alcohols and make them into carbonyls. This is an oxidation. Probably the nicest reagent to do this is called PCC because its real name is pyridinium chlorochromate. Looks like this. It's a nice, stable, gentle, specific oxidant. What you need to remember is simply PCC and dichloromethane, standard oxidizing conditions. take your OH and you make it into a carbonyl. It works for primary and secondary alcohols. It's probably the nicest way to do it. Now, just like the sulfuric acid reaction, there are also ways to do this that are not so nice. Call it Jones reagent, if you will. This is a simple chromate in sulfuric acid. This will work with secondary alcohols only to give ketones. If you tried to do this oxidation with a primary alcohol, it would take it all the way to the carboxylic acid. The bottom line, chromate is not very good unless you want to make carboxylic acids. PCC is probably your best choice. And finally, there's one other reaction that is acute, very specific only for allylic alcohols. This is one of the very rare ways that you can easily make an aldehyde. If it's an allylic alcohol, that is next to a double bond, just simply MnO2 and pentane will convert this very smoothly into the aldehyde. It's only specific for allyl alcohols, but if that's what you have, it works very nicely. Let's just do a couple quick oxidations here.
Allylic is when it's next to, when it's attached to a carbon that's adjacent to a double bond, right?
Right. When you see chromate, you think, oh, that's strong. Ever heard of cleaning solution? I mean, when you really muck up glassware badly and you just want to dissolve anything that's in there, you use chromate and sulfuric acid. So it really is a strong oxidizing agent. Well, chromate and sulfuric acid, primary alcohol, it's going to go all the way down to the carboxylic acid. Gee, that's PPC. That's supposed to be PCC, I'm sorry. Oops. But we know that PCC and dichloromethane is a very nice, smooth oxidizing agent. We have a primary alcohol that will make it into an aldehyde. And our last one, again, chromate, sulfuric acid, very strong. But we have a secondary alcohol here. So it will work with secondaries
Jones,
and make the ketone.
Jones reagent.
Jones reagent, right? Or cleaning solution. PBr3, thionyl chloride. Go ahead and do these. Remember, they will convert the alcohol into an alkyl halide. PBr3 reacts, we form a phosphide ester. Get an SN2 reaction, but we have no stereochemistry here. We simply replace with the bromine. You don't have to draw it like I did. I'm just compulsive, but
So it can be at the same location.
now the next one you do have to think about, because we have stereochemistry here, don't we? Hydrogen is back, methyl is forward, phenyl group, and the OH. Dinyl chloride and pyridine, that gives us inversion, doesn't it?
Yeah.
So we need to draw our product inverted. Simplest way to do that is just to take our group that's coming forward and move it back. What we've done is swap the position of the hydrogen, which used to be back, methyl was forward. Now the hydrogen must be forward because we've defined the methyl as back. Inversion of configuration. Finally, our dimethyl cyclohexanol. Simple inversion, but it doesn't matter because it's not a stereocenter, right?
Okay.
Oh, I put the hydrogen in here just so you can see that. See, hydrogen back, hydrogen forward, methyl back. And this guy, all you do is replace the bromine. POCl3 and pyridine, that's going to give us an alkene, isn't it? PBr3, inversion of configuration. HCl and ether, carbocation intermediate. Quickly draw the products. All right, we're going to form our chlorophosphate ester here. Going to do an E2 elimination. That means we're going to make an alkene. It's an E2 elimination, so we're just going to lose our OH. Going to wind up with our terminal alkene here, looking like that. We have stereochemistry. We have to worry about it. Simplest way is just to take and swap the configuration, right?
Mm-hmm.
So if our OH is forward, all we have to do is draw our product with our bromine going back. And this last one works because the carbocation we'll get here will be a benzyl carbocation, right? And that's nice and stable. That will just add our chlorine. Whoops. Okay. I suppose I should have drawn this as the halogen. We also do get elimination here, but we haven't talked about that one. So I apologize for that structure. Go ahead and just do that as the benzyl chloride. Yeah.
For the reactant prior, CH3 stays like both, stays in the front.
Yeah, yeah. No chemistry happens there. So the inversion happens only at the alcohol center.
Okay.
All right, two more here quickly. We're doing PCC and dichloromethane. And again, we're doing Jones reagent. Primary alcohol is going to go to an aldehyde, isn't it? So the carbon bearing the OH is going to be a carbonyl, and it will be a simple aldehyde. And finally, we're using Jones reagent here, and we have a primary alcohol. We know that we're not going to stop at a carbonyl, are we? It's going to take it all the way to the carboxylic acid. So this is going to be a carbon-oxygen double bond, bonded to an OH. All right, the reactions of this chapter just keep going. Like I said in my morning email, this chapter can be overwhelming. So let's continue our process of being overwhelmed here. And let's talk about the notion of protecting groups. We're going to use protecting groups both in alcohols, and we'll do it again in chapter 19 when we're dealing with aldehydes and ketones. Protecting group. Let's say we had this stuff when we were trying to make this stuff. Okay? Let's just pretend. Well, you would say, okay, I can convert this carbon-bromine bond into this by making a Grignard and reacting it with formaldehyde. But remember, you can't do a Grignard if we have an acidic hydrogen. So this won't work. What we do is we protect the OH group. We want to add something to it so it doesn't react anymore. Then we want to get rid of it. If we tried to make a Grignard, this OH would react with the reagent. It'd be ruined. Wouldn't work at all. So, there are two ways that we do this. One is very simple. This is chlorotrimethylsilane. You really don't have to worry too much about it, but the silicon here can undergo an SN2 reaction with an alcohol to form a silyl ether. Now the silyl ether is very stable under basic conditions, but in the presence of acid, it just falls right off. Well, the Grignard reagent is very basic, isn't it? It's a carbanion. So once we make this stuff, we can convert this to the Grignard. Add formaldehyde and stick on our CH2OH. What's the last step of every Grignard reaction? You dump it into acid, don't you? This stuff falls off, and you've got your product. the concept of a protecting group. You hide a functional group, do your reaction, and then get rid of it. With alcohols, there are two ways to do this. This is the simplest. Using chlorotrimethylsilane is a little tricky. This one is actually a simpler reagent, but we don't quite understand all the chemistry here yet until we do chapter 19. If we take dihydropyran, it's called. It's an alpha-beta unsaturated ether. In the presence of acid, we can form this, what we'll call a ketol in chapter 19. Again, this is very base stable. The reason this happens, again, if we dump it in acid, we can cleave it off again right away. The reason this works is that dihydropyran exists as two resonance forms where we have a carbocation here next to the oxygen. And so that's why this oxygen will add to it to form this stuff. The actual chemistry of the whole thing is a little bit beyond what we know yet, so we're not going to go into detail. But remember, we can protect the alcohol even with chlorotrimethylsilane. We'll use this reagent when we get to chapter 19. We also know from way back in chapter 6 how to make 1,2-diols, right? Well, one of the neat things about 1,2-diols is that we can split at the bond in between the two oxygens simply using iodate. It's just an acid. We're going to split it right here. Both halves wind up as aldehydes. The reaction involves formation of this intermediate with the periodate. This is the bond we're going to cleave. It's done by magic. Wind up with periodic acid, and again, two aldehydes. It's actually a very useful reaction. This is the classic example of it. It's actually a very important example of it. Look at this diol and predict the cleavage product form. Very important industrial reaction. Well, the bond you're going to cleave is between the two oxygens, right? We're going to cleave that. We're going to make both of these into aldehydes. This is our periodate ester. And once again, this is the bond that we cleave. It's done by magic. Our product is hexane dial. Now we're actually going to do this lab, not this part of it, right at the end of the semester if we have time. Why is hexane dial important? Well, because if we react this very simply with 1,6-diaminohexane, do you know what you make? Nylon. This is how nylon is made industrially, how it was first made, and it's our classic example of a synthetic polymer. Now there's one more example of a reaction of a 1,2-diol that I want to put up just for your own benefit. It's called the pinnacle rearrangement. reason that I'm doing this is because sometimes on standardized exams, think, MCAT and whatever, chemists like to put in things like chemical rearrangement. So you should understand that this reaction does exist. We won't revisit it on an exam, but just make sure you know that the reaction exists, okay? This is phenol. That's its trivial name. It's a butane with 2 methyls and 2 hydroxyl groups. The rearrangement was discovered when they tried to dehydrate this in the presence of acid. So you could argue that if you put this in acid, you could protonate this to an E1 elimination and form a double bond here. Reasonable, right? Well, here's our protonation product. But what happens here is we do not get elimination across here. Instead, once we form our carbocation, we get the classic example of a 1,2 methyl shift. Remember we did hydride transfers? We can do methyl transfers too. The methyl group with its electrons just slides from here to here. That's our intermediate. Lose the proton, and we make a carbonyl. This is what's known as the phenol rearrangement. Again, you cannot do dehydration on 1,2-diols because they will do a phenol-like rearrangement. Any questions? All right, well, I promised you that this was going to be an overwhelming chapter, and I did not lie. Let's just quickly review some of the reactions we did. Go ahead and jot down these products. See, this is a real problem with trying to do an entire chapter in one period. This is just brutal, both on you and me, to be honest. Yeah. Yeah, if you do it over 3 days or so, it goes in a lot easier, I assure you. Carbonyl, sodium borohydride, reduction, we know that. All you're going to do is add H- to the carbonyl carbon, and we will have the alcohol. Grignard, we have an ester. Going to add 2 of them, aren't we? So we're going to put 2 methyl groups on this carbon. This is going to be an OH, 2 methyls, and a phenol. Lithium aluminum hydride, going to add H-. This is going to convert our ketone here into a secondary alcohol. Any question? PCC and dichloromethane, we love this reagent. It will convert alcohols smoothly into carbonyls. Secondary alcohol, we're going to make a ketone. Grignard, aldehyde, secondary alcohol, right? On one side, we will have our phenyl group. This will be an OH. On the other side, we will have the cyclopentane attached. And finally, phosphorus oxychloride, POCO3. This is going to be our E2 elimination, isn't it? We'll make the ester. We will eliminate across here, trans elimination, E2 stereochemistry to make the alkene. Now the last bit in this chapter is just thiols. Thiols stink. Butane thiol is the essence of skunk. Thiols are just below oxygen on the periodic table. So a thiol is simply an alcohol wannabe. It does the same chemistry, except it's better at it, actually. We could call this butane thiol, cyclohexane thiol, benzene thiol. This stuff really smells. It gets into your system and it's with you for 6 months. If we have two functionalities, instead of calling it a thiol, we refer to this as a mercapto group. So this is mercaptoethanol. In biochemistry, if you are fortunate enough to take biochemistry in biochemistry lab, you will use mercaptoethanol when you do gel chromatography. Or electrophoresis, it reduces disulfides. It also stinks. Just a couple reactions. To make a thiol, we could take a simple alkyl halide and do an SN2 reaction. Sulfur is a much better nucleophile than oxygen because it's lower in the periodic table. So all that happens here is we get attacked. This is gone. SN2 chemistry to make the thiol. There's also a very complicated way to do it, using what's known as thiourea. We're going to make an alkyl isothiourea salt. Don't really have to know this reaction, but it's kind of cute. Again, the sulfur is a great nucleophile. It will attack. This is our this is the salt. Once we have this, we can cleave this off just with base. And again, we wind up with our thiol. The last thing you should remember about thiols, remember when we did nucleophilic aromatic substitution, the one example we did was with hydroxide, right? Well, it turns out that because sulfur is such a good nucleophile, it is really, really good at this reaction. It's a great thing. You can add your thioether to a deactivated ring. Very, very sweet. All right, now I know that there's a huge amount of information here.